All right, we're starting with chapter 6 for this semester. So, clean slate, semester 2. We're starting with chapter 6, and we're really getting into chemical bonding. So, the different types of bonds, how they form, and what elements each kind of bond makes, or what they're made of. So, I'm going to pause the video just a second and have a question come up that's the same as this slide. So, you're just going to list a few things that you've learned so far in chemistry about atoms and what they're made of. So, try to really think about what we've talked about so far in chemistry, subatomic particles, maybe think of the periodic table wall to start thinking about what you could put for this question. All right, so we've seen some of these things before, but we're just going a little more in depth with them. And I have the screen split because I'm going to need that periodic table in just a minute. All right, so an ion, which we've talked about before, but we're really getting into what ions are, how they form, and what elements make ions. So if an atom of whatever element gains or loses electrons, or it has a different number of electrons than it should, it's called an ion. So groups 1, 2, and 13, and the transition metals, so those ones that are in the blocks 3 through 12, on the periodic table, they lose valence electrons. So if you remember, valence electrons are the electrons on the outermost ring. So if you're looking at this example over here, this electron, this electron, this electron, and this electron are the valence electrons because they are on the outermost ring. So groups 15, 16, and 17 on the periodic table tend to gain electrons. Remember, they're all trying to get to 8, except for a few, which we'll go over in just a minute. So a chemical bond is an electrical attraction. It's mutual for these atoms to combine together to have an overall neutral charge. So now we're going to look at the periodic table, and we started to do this right before break, but we didn't get too far into it because I knew it when second semester started, we really dive into this, but I wanted to introduce it before we went on break. So valence electron determination. So again, the valence electrons are the electrons in the outermost ring. So you don't have to draw those Bohr models like we were doing at the beginning of the year where you had to move the electrons and all that. There's a really easy way to figure out how many valence electrons. So I've already labeled this on here. So everything in this column has 1 valence electron. Everything in this column has 2 valence electrons. We skip group 3 through 12 because they have what's called a d orbital, and the valence electrons vary. So we're going to skip groups 3 through 12 for now, and we'll come back to them later when we start naming compounds. So then group 13, so this whole column has 3 valence electrons. This whole column has 4. This whole column has 5. This whole column has 6. This whole column has 7. And then this whole column has 8 valence electrons. So I have a smaller periodic table over here, and you can open the periodic table that's linked into your notebook, your chapter 6 notebook, but I'm just going to use the periodic table that's small and it's on your slides. So we're just figuring out how many valence electrons each of these has. So I'm going to do a few, and then the rest are going to be questions in this video that you have to answer, and then you have to complete all of them because I'm not sure how many questions it'll let me add to this. You want to make sure this is all done in your notebook, but answer the few that are in this video too. So let's look at chlorine. Chlorine is right here, which I'm just going to circle these because I can clear it later. Chlorine's right here. This column, this whole column, if you look back over here, has 7 valence electrons. So chlorine has, I'll just put in equals, 7. All right, then we're going to look for Be, which is beryllium, which is right here. Beryllium has 2 valence electrons, so 2 electrons on the outermost ring. K, which is potassium, is right here, has 1 valence electron. Si, which is silicone, is right here, has 4. And then oxygen, which I'll do 2 more after this one, is right here, and it has 6 valence electrons. Then we have to look for helium. Helium is right here, and this one's tricky. So helium, technically, we would think 8. But helium only has 2 electrons. Just like hydrogen has 1, remember this is the atomic number that's at the top. The atomic number, the number of protons, and the number of electrons are always the same, unless we have ions, which we're getting into now. Helium doesn't even have 8. The most that it can have is 2. So if you remember when we were talking about, or we were drawing those Bohr models, I will just draw a small one over here. We did the first ring, and then there was the second ring, and the max amount of electrons that could fit in the first ring was 2, and then the max amount of electrons that could fit in the second ring was 8. Helium has 2 in its first ring, so let's turn that into an electron. It has 2, and this ring can't hold any more. So it's technically a stable atom by itself, helium over here. And that's why it's put in this column with these other noble gases. Remember, they have full outer rings. Majority of these have 8 in their outer rings. Helium is the exception. And that's why it's listed right here instead of over here by hydrogen. So helium has 2, and that's the only one that's kind of funky with that. All right, let's look at lithium. Lithium is right here, and it has 1 valence electron, so 1 electron in its outermost ring. All right, I'm going to pause this, and then it's going to ask you for the next few number of valence electrons for each of these different elements. All right, this is the ion worksheet. We did this before, but there were a lot of issues. So I'm going to go through this just to get everybody on the same page. And if you understood it, this will be a really great refresher for you. All right, so we're still looking at valence electrons, but now I want to make sure we're on the same page because we're getting into chemical bonding. And if you don't understand chemical bonding, it kind of sets you up for a disaster for the rest of the year. All right, so we're going to start with the element Na. So you look on the periodic table over here. Na has 1 valence electron. So remember, all of these, except for hydrogen, are trying to get to 8. They want a complete outer shell or a complete outer ring. In order to do that, most elements want 8. They can either gain electrons to get to 8, or they can lose electrons to get rid of their outer ring, and then they have a full inner ring. So for sodium, it has 1 valence electron, and it wants to get to 8. It can either gain 7, or it can lose 1. Now, atoms are just like us, kind of. They're going to take the path of least resistance. It's a lot easier to give up 1 electron than to have to gain 7 individual electrons. So sodium is going to lose 1 electron. And we write electrons with a little e. So remember, electrons are negative. They have a negative charge. I'm going to write that up here just so we can remember. If an atom is losing something that's negative, the atom is becoming positive. So its charge, or sodium's charge, is going to be a +1. So the total number of electrons is we have to look back at sodium. So yes, sodium has 1 valence electron. In total, it has 10 electrons. There's just 1 on the outer ring, or 11 electrons. There's just 1 on the outer ring. So if sodium has 11 and it loses its 1, it will now have 10 because it's trying to become like a noble gas. The noble gas that it's trying to become, we look for the atomic number 10 because it would also represent the number of electrons, is neon. So sodium is trying to become like neon and have a full outer shell like neon does with 10 electrons. All right, magnesium. So we go back over here, and this makes a dot every time I have to click back over. Okay, magnesium has 2 valence electrons. Now magnesium wants to also get to 8. So it can either gain 6 or it can lose 2. It's just easier to have to lose 2. So it's going to lose 2 electrons. So if it's losing 2 things that are negatively charged, it's going to have a positive charge because the atom is gotten rid of some negatively charged things. So it will have a +2 charge. So in total, over here, magnesium has 12 electrons. If it loses 2 of those, it will have 10. The atom that has 10 electrons, again, is neon. All right, let's look at aluminum. Aluminum is over here, atomic number 13. It has 3 valence electrons. Now, aluminum can either gain 5 to get to 8, or it can lose 3. So again, it just takes the path of least resistance. It's going to lose 3. If it's losing 3 negatively charged things, the atom is going to have a positive charge and it's going to have a positive 3 charge. So in total, aluminum has 13 electrons. If it loses 3 of those, it now has 10, which the atom that has 10 electrons is neon again. All right, silicone is kind of tricky, but not too tricky. So silicone is atomic number 14, and it has 4 valence electrons. So silicone can either lose 4 or gain 4. They're both equally as challenging, or silicone's more likely to do either one. So this can go both ways. So I'm going to put lose or gain 4. So if it loses 4, it will have a +4. If it gains 4, it's going to have a -4. So silicone, if it loses 4, in total, silicone has 14 electrons. If it loses 4, it will have 10 electrons. So this could be 10, and that would be like neon. If it gains 4, so it's 14. If it gains 4 more, it would have 18 like argon. So we'll put or 18. A little bit of slash because I'm going to run out of room. Argon. All right, phosphorus. So phosphorus is right here. It's right next to silicone, atomic number 15. It has 5 valence electrons. So phosphorus can either gain 3 to get to argon, or it can lose 5. So in this case, it's easier to gain the 3. So if an atom is gaining 3 negatively charged electrons, and I'll put electrons here, it's going to have a negative charge. So this is going to have a -3 charge. So then we look back at phosphorus, and if it has 15 total electrons and it gains 3, it now has 18. And the element that has 18 electrons is argon. All right, sulfur. So sulfur is atomic number 16. It has 6 valence electrons. So sulfur can either lose 6 of those valence electrons to go all the way back to neon, or it can gain 2 to get to argon. And which you just think of which one seems easier. So it's easier for sulfur to gain 2 electrons. So if it's gaining 2 negatively charged things, it's going to have a -2 charge. So in total, sulfur has 16 electrons. If it gains 2, it will have 18 like argon. All right, chlorine. So chlorine is atomic number 17. It's right here. It has 7 valence electrons. So chlorine can either gain 1 to get to 8, or it can get rid of 7. But the easier one and the most likely outcome is for chlorine to gain 1 electron. So if it gains 1 electron, it will have a -1 charge. So chlorine right here, if it gains 1, it will have 18 electrons total, which is like argon. All right, bromine, which is right underneath chlorine, atomic number 35, has 7 valence electrons. So just like chlorine, bromine is going to gain 1 electron. And it will also have a -1 charge. However, the noble gas is different. So for bromine, it has 35 electrons on its own. If it gains 1, it will have 36. The element with 36 electrons is krypton. So we put 36 here, and it is becoming like krypton. All right, oxygen. So oxygen is all the way up here. It has 6 valence electrons. So oxygen can either lose 6 or it can gain 2. And the easier of those two is to gain 2. Gain 2 electrons. If it's gaining 2 negatively charged things, it will have a -2 charge. So then we go back to the periodic table. Oxygen is right here. It normally has 8 electrons, but if it gains 2, it will have 10, like neon. All right, last one, calcium. So calcium, which I don't even have to click over, is over here, number 20, and it has 2 valence electrons. So calcium can either gain 6 to get to 8, or it can just give up its 2. And the easier of those two is to lose 2 electrons. Now, if it's losing 2 negatively charged things, it will have a +2 charge. So calcium's right here, and it normally has 20. And if it's going to lose 2, it's going to go to 19 and then to 18. So 20 minus 2, which would bring it to 18 total electrons, which is like argon. All right, and that's how we figure out what noble gas these are becoming like. So the atoms, or the elements that lose electrons or give up negatively charged things, they become more positive. And we've seen these definitions before. So when they give up those electrons, they become more positive. Those are called cations. Elements that gain electrons or add negative things to them, they are negatively charged atoms. They're called anions. So we have cations and anions. An ionic bond, so when these ions form, they are a result of atoms coming together by either giving up their electrons or taking these electrons from other atoms. So if we look on this periodic table, which I pulled up a separate periodic table over here. Oop, that's electronegativity, not what I wanted. So everything, and you can see this little stair step I have going on here with the down, it goes through boron, silicon, arsenic, tellurium, and then polonium. Everything to the left is something that is going to give up electrons. So it's going to be more positive. Those are the cations. Everything to the right is considered an anion. They are going to, except for tellurium and polonium, don't get those mixed up. Everything to the right is going to become an anion. They are going to take electrons. And that makes sense because like hydrogen, lithium, and sodium, they want to give up their electrons and they want to be positively charged. So they are going to bond with things like fluorine and chlorine and bromine and sulfur and oxygen, because like lithium wants to give away its electrons, but at the same time, fluorine is willing to take those electrons from lithium. So if we have two things, one thing from the left side and one thing from the right side coming together, that would be an ionic bond, because one's giving up its electrons and the other is taking. So those were ionic bonds. Now we have covalent bonds. So instead of electrons being taken or given up, we have another type of bond, a lot more friendly bond. So covalent bonds are when electrons are shared. They're equally distributed between the two elements and they're shared. Now, ionic bonds are like aggressive and they're really strong. Covalent bonds are also strong, but just not as strong. They're a very friendly, willing to share their electrons. And here's just a picture I have. It's from your textbook, more of like a chemical viewpoint of what covalent and ionic bonds look like. All right, so I want to make sure we have this really, really, really well understood. So let me pull that periodic table back up. So if you remember when we were talking about the different groups, like the noble gases, the halogens, alkali metals, transition metals. So with the exception of arsenic, tellurium, and polonium, so disregard those, keep sulfur and boron in your mind. Everything to the left of that stair step is considered a metal. Now, when you're thinking of a metal, I know you're thinking of steel and things that hold up buildings and very tough, hard structures or components of whatever material you're thinking about. Metals are different, have different properties. So potassium, which is atomic number 19, is considered a metal because metals have a bunch of different properties. They're not just things that, hold up buildings and make tools and all kinds of things like that. And so is calcium. These are all metals. Everything to the left of this stair step right here is considered a metal. And that includes lanthanides and actinides at the bottom. Everything to the right is considered a non-metal. So carbon, obviously, non-metal. These are things that we breathe. So metals are typically cations. They form positive ions. They give up their electrons. Non-metals, so carbon, nitrogen, oxygen, chlorine, all those, they tend to form anions. They tend to take electrons. An ionic bond, remember from the previous slide, is a bond between an atom that is going to give up its electrons and an atom that is willing to take those electrons. A covalent bond is between two non-metals. So anything to the right of this stair step is going to be considered a covalent bond. And that's important that we know the difference between those, because when we get to naming and predicting the products of a reaction, we have to know what kind of bond is going to form, and do these elements actually come together? So in ionic bonds, the kinds of elements that are involved are typically, or if we're talking about one specific compound, it is a metal plus a nonmetal. And in covalent bonds, remember there's no stealing or giving up electrons. They share, which is the next part of this question. So in covalent bonds, this is two nonmetals. So we will have a nonmetal plus a nonmetal. And I want to point out something very quickly. It doesn't become relevant for a couple sections. Hydrogen is not a metal. Just like helium over here, that is a nonmetal, but helium is here in line with these noble gases because of its full outer shell. Hydrogen has one valence electron, and that's why it's in line with all of these other elements over here, but it is not a metal. So in an ionic bond, the electrons, so they are transferred. They're transferred between the elements. So let me give you an example. If we had a bond between lithium and fluorine, let's just, for example, so Li and F, lithium it has 1 electron, so we'll put a 1 here. Fluorine has 7 valence electrons, and all the bonding that goes on, it happens with the valence electrons. So lithium is going to give up its 1 valence electron and give it to fluorine, so that way it has 8. Lithium wants to give up its 1 valence electron, so that way it can become like helium. So lithium is going to give up its electron to fluorine, and that's what creates that bond. Fluorine's constant pull on that 1 valence electron from lithium. And then in covalent bonds, the electrons, I'm just going to use the abbreviation, the electrons are shared. So there's no pulling. We'll talk about dipoles in a few minutes, but the electrons are shared. Nobody's pulling and trying to yank and give up or take electrons. So here, and I just gave you an example of what would be a ionic and an ionic bond, and it just happens to be the first example on this slide. So we're going to look at the periodic table over here, and we're going to determine if it's a metal or it's a non-metal. Actually, this one is better. I like this one better. Move it. Here we go. Okay, so we're going to break these compounds down. So we have Li and F. So the symbol of the first element in this compound is Li. And the symbol for the second element in this compound is F. So now we have to figure out if Li is a metal or a non-metal. So I can't draw on this specific periodic table, but remember everything to the left of that stair step is considered a metal. So I'm just going to put M, because lithium is considered a metal. Now we have to look at fluorine, or the symbol F, which is right here. This is considered a non-metal. So I'm just going to put non. So we have a metal plus a non-metal. A metal plus a non-metal is an ionic bond. All right, the next one, and I'll do the first few and then I will give the rest to you. So the first symbol is Na, and we look on the periodic table. Na is all the way atomic number 11, it's all the way on the left side. Na, or sodium, is considered a metal. Our second element is Cl, which is atomic number 17, all the way over here. That is a non-metal. Again, we have a metal plus a non-metal, which is an ionic bond. All right, O3, which is ozone. So technically, if we were going to write out this bond, it would look like this, 3 oxygens. We technically should add another box that would say third element, but it's all oxygen. So it's okay if we just use oxygen twice. So the first symbol is oxygen and the second symbol is oxygen. Oxygen is in atomic number, it's atomic number 8, it's in group 16, and it is a non-metal. So we have a non-metal plus a non-metal. Non-metal plus a non-metal is a covalent bond. All right, HCl. So our first symbol is hydrogen, and I don't have to click on this over here. Remember I said hydrogen is not a metal. It's only here because of its 1 valence electron. So this is a non-metal. And then we have chlorine. So chlorine was up here in NaCl, and that was a non-metal. So we have a non-metal plus a non-metal. This is a covalent bond. All right, I'm going to give the next 3 to you to do. All right, this did not save well on mine. However, there's another way to determine what kind of bond we're talking about. So on your notes, I have this. The table didn't show up like this on yours. It's not like that on yours. It's only like that on mine. But we need to determine the electronegativity. So we're determining how likely or how strong a pull an atom might have to draw in other electrons. So I'm going to pull up the electronegativity sheet, which this is also linked in your Chapter 6 notebook, and I linked it in the notes as well. So elements that, or the electronegativity is the ability of an atom to pull electrons towards it. So we would expect elements on the right side of the periodic table or the nonmetals to have a higher electronegativity or a greater ability to pull electrons in. And elements on the left side, or the metals on the left side of the periodic table, to have a lower electronegativity because they don't want to pull in electrons. They want to get rid of them. Now, they still have electronegativity because there's always exceptions to all of these. We get into some of them, not all of them. But they don't really want to pull in electrons. They would prefer to get rid of them. So, move this over. If we go back to here, anything with an electronegativity difference between 0 and 0.30 is considered a nonpolar covalent. And I need to get this out of here so I can show you what that means. You can see this underneath. If anything has a electronegativity difference, and we're going to do practice problems in just a second, greater than 0.30 and up to 1.7, that's considered a polar covalent, and anything above 1.7 is considered an ionic bond. So covalent bonds, remember, they share electrons, but they're always sharing. Sometimes it's just a little bit more uneven. So a bond between chlorine and chlorine, which I got the 4.00 from here, that should be a 3.00 on yours. This 3.00, before you get confused, let's get that out of there. So 3 and 3. So the difference between these two is 0, which again, we're going to do examples in just a minute. These electrons between this chlorine-chlorine bond are equally shared. There's perfect sharing going on. However, a bond between hydrogen and fluorine has an electronegativity difference that would put it in a polar covalent. So this chlorine-chlorine is considered a non-polar. So there's no poles you can think of. There's nothing pulling on the other one. However, this bond over here, which is two nonmetals still, so it's covalent, the fluorine has a higher electronegativity than hydrogen. So fluorine, although still technically sharing, is pulling those electrons from hydrogen just slightly more. In an ionic bond, they're pulling completely or giving up completely. In a polar covalent, there's one slightly more negative end, which in this hydrogen fluoride compound, fluorine is the one that's pulling a little bit more. All right, so instead of just looking at, okay, arsenic is a nonmetal and sulfur, or arsenic is a metal and sulfur is a nonmetal, that's the kind of bond, we look at the electronegativity, because on that stair-step periodic table that I was showing you, it's not always clear. There's a gray area with the metalloids group. So I attached this electronegativity sheet to your notes and in your notebook, your Chapter 6 notebook. So we look at the electronegativity for each element. So arsenic, which is As, is right here. It has an electronegativity of 2.12. And sulfur has an electronegativity of 2.46. So we subtract these, and the answer is always in absolute value. So I'm going to put absolute value bars on this symbol up here. This is the electronegativity symbol. So when you do the subtraction, you get, it's negative 0.34, but since it's absolute value, it is 0.34. So let me go back to the previous slide. So the electronegativity difference, 0.34. That fits between this polar covalent, right? Anything bigger than 0.3 is considered polar covalent. I'm going to write this as small as I can. So this is a polar covalent bond, which means that sulfur, because it has a higher electronegativity, this is a covalent bond and they're sharing electrons, but sulfur is just ever so slightly pulling those electrons just a little bit more than arsenic. All right, this next one, cobalt, so CO is 1.79. And bromine, which is 2.82. When you subtract those, again, it's absolute value, so it's 1.03. So that, if you go back to this previous slide over here, anything between 0.3 and 1.7 is considered polar covalent. I'm just going to do this so I don't have to rewrite it and to make a super long video. The next one, germanium, which is right here, is 1.93. And selenium, which is SE, is 2.45. And this comes out to 0.52, which is also, if you go back to that previous slide, in the polar covalent. So I'm going to write that little ditto mark. All right, this next one is silicone, so Si, which is 1.94. And fluorine, which is 4.00. So that subtraction gives you 2.06. So that is well above 1.7, and that is an ionic bond. So potassium, which is right here, I don't even have to click that, is 0.84. And nitrogen, which is 2.81. And when you subtract those, you get 1.97. And again, that's well above that 1.7. So this is also an ionic bond. All right, lead, which is Pb, and it's all the way down here, is 1.87. And oxygen, which is all the way up here, is 3.37. All right, that subtraction is 1.5. Now that falls between the 0.3 and 1.7, so that's a polar covalent bond. All right, and I want you guys on your own or in this, you'll have to complete it in your notebook, but I want you to complete it for this video question also. You're doing the same thing, and these are your practice problems right here. Once you finish that, this is the section summary, just so we understand the difference between ionic and covalent bonds. So at the end of your notebook, or the section 6.1, there's a space, and I've put a little text box on there that says answer the section summary here. You're going to describe the two kinds of bonds. So you're going to describe an ionic bond and you're describing a covalent bond. But I don't want you to use words, and I don't want you to use this example right here. You're going to find your own. You can use GIFs. You can find TikToks. I added pictures because I can't embed these right here between the Google Slides and the PowerPoint. It won't go over the same. But get creative. So the example that I used is the Grinch being greedy, and it took all the presents from the town of Whoville. And in ionic bonds, electrons are taken by certain atoms. In covalent bonds, the electrons are shared. So Lady and the Tramp, they're sharing the spaghetti. This example is taken. But if you can find TikToks, I know that's like the super cool thing right now, or if you could find GIFs, that would be cool too. And then just add them to the end of your section 6.1 notebook.